Well, thanks a lot for inviting me to give a talk here today. So the title of my talk is, I'm actually just trying to see if I can see my own screen here. Hang on a sec. The title of my talk is basically looking at microbially enhanced geologic carbon and gas storage from the laboratory to commercial application. Just to thank all of my co-workers here. This is work that's been, as I'll explain, been going on for quite a number of years now, work between ourselves, Aberystwyth, and also at Montana State University in the Centre for Biofilm Engineering. What I wanted to also highlight is that I'm from a group which is myself and my co-worker Arwyn Edwards run, and we're interested in really looking at microbes in the natural environment, but also looking at ways in which we can manipulate them for various gain. This includes microbes and energy resources, various subsurface biotechnology, and also we have a particular interest in glacial environments and biotechnology. I'm not going to be talking about the glacial stuff today. I'm more going to be talking about microbes and carbonate mineral formation. Now, this is something that I've been really working on for quite a number of years, and specifically looking at the role of bacterial ureolysis as a way in which we can manipulate carbonate mineral formation. We call it microbially induced carbonate mineral precipitation. We're talking about mineralization that occurs extracellularly, and in a sense, the exact role of the cell surface and the microbe-mineral interface is not as clear as we might think, and we'll have a little bit of a discussion of that through the talk. And also really today, I just want to talk about a story really from the lab to the field to the commercial application. I know a lot of us work on things that, you know, we always argue are for engineering use, for applied use, for solving environmental problems. But the reason I wanted to talk about this one today, really, which has been, you know, one of the strands of my research for a number of years, is really because we've gone all the way from the lab now to commercial application. So I just wanted to share some of that with you today. Just in relation to that, I thought it'd be interesting to really look at this, because if we actually look at publications related to carbonate precipitation and ureolysis, which is basically urea hydrolysis induced carbonate mineral formation, we really see an exponential increase in the number of publications from the late 90s all the way through to present. And really this has really reflected a shift in studying ureolysis and carbonate mineral formation in medical settings, in natural environments like soils, through to really work in the late 90s. And this is where I became involved. Grant Ferris, who many of you know at the University of Toronto, developed really the concept of manipulating this process to induce calcium carbonate formation for controlling permeability, mainly in relation to enhanced oil recovery. And this then led on to work initially investigating this process for co-precipitating contaminants like radionuclides. And the rationale for this was that this might offer a way in which we can manipulate bioprecipitation to really reach hard to reach subsurface environments, because really this really only requires inexpensive non-viscous fluids. And as I'll show you, the gradual ureolysis and mineral precipitation that we can induce avoids the instantaneous chemical precipitation that you get from simple inorganic chemical precipitation reactions. And really in the last decade, the research in this area has really ballooned. As I say, it's going from around 20 papers per year in the early 2000s up to now, up to around 3,000 papers a year on this topic. So it's an absolutely massive area of research now, mainly because of the wide range of applied use, from soil stabilization, biocement, dust suppression, and many other processes. And today I'm really going to be talking mainly about contaminant co-precipitation, and then moving on to our work looking at using this process for enhancing carbon storage during geologic carbon sequestration, mainly to do with reducing potential gas leakage. This is just a review paper we did a few years ago, really just highlighting, you know, the various roles of microbially induced carbonate precipitation in the engineering world. So it's really been, utilized in a number of different locations, or at least in a research world. But as I'll go on, in a sense, not so many of them have necessarily gone on to commercial application. So what's the actual process? What are we talking about when we're talking about, I call it MICP, using ureolysis? Well, effectively, we're inducing, we use a model organism often, Sporosacina pastori, which is a urease-producing organism. And the process is rather simple. We feed it urea. The hydrolysis of urea, catalyzed by the urease enzyme, produces carbonate and hydroxide ions. That ramps up the pH. You've then got free carbonate in solution, which can then precipitate with any free calcium in solution, thus forming the carbonate mineral. So that's really the principles of what this particular process is. And as I said, it's a nice simple process which is why in a way it's been studied so widely as a way of manipulating biologically induced mineralization for various engineering purposes. This is just a simple diagram I just put together today just to really highlight, this is what we see in simple microcosm experiments, because this is really where it began. Simply working on static microcosms with the Sporosacina pastori and basically observing what happens. And the overall reaction is rather simple. We see an increase in ammonia production through the hydrolysis of urea. We also see an associated increase in DIC and pH. And at the same time, we see a decrease in the free dissolved calcium concentration due to the precipitation of calcium carbonate. So it's a rather simple process. And much of the early work really was done in microcosms. So this is really looking at diffusion-based processes, okay? Now, this led on to work investing contaminant co-precipitation in these microbial carbonates. This is really based upon, obviously, the realization that strontium and other potentially harmful elements can coordinate quite well in the calcite mineral lattice in particular. And as I mentioned, using this particular mechanism, it offers a way to form carbonates in rather hard to reach subsurface zones, because it really only requires the use of low viscosity fluids, and controlled gradual precipitation avoids this inlet plugging issue that we would have if we were using simple chemical mixtures. So here's some of the radionuclide work we did a lot of years ago, really just looking at how we can successfully co-precipitate strontium as a proxy for strontium-90, which is a common fission byproduct, which has a kind of rather problematic half-life of 29 years, and how we can co-precipitate this in carbonate minerals. We saw that the process the rates of precipitation are increased with temperature. No great surprise there. And we also see that critical saturation and precipitation broadly occurs at the same critical saturation and ammonia concentration under a range of conditions with or without the inclusion of strontium. We broadly see that reaction rates are proportional to the saturation state for calcite. And over the experiments we see, and this is the general sort of data we're getting, we see that saturation and rates thus decrease over the duration of the precipitation event. And when we look at how effectively strontium can co-precipitate within the structures, we see that precipitation, which is derived here as the homogeneous homogeneous partitioning coefficient, we generally see that increases with the reaction rate. So larger precipitation rates lead to a greater magnitude of strontium co-precipitation relative to calcium co-precipitation. Okay. Now we see that that's broadly due to higher reaction rates favoring the incorporation of strontium relative to calcium due to more indiscriminate ion incorporation at higher rates. And we also see larger co-precipitation and greater partition coefficients at higher temperatures, which is broadly due to the higher miscibility of ions at higher temperatures. Now, in these unseeded experiments, we generally see that rates are quite low as equivalent saturation states compared to many seeded abiotic experiments. So it seems that, even though we've got cells in there, we've got a low surface area, despite the cell, which are potentially acting as nuclei within these experiments. And this really leads us just to start thinking about what's the specific role of the cell surface in this reaction, and really the cell mineral interactions. So if you saw Jeff's talk yesterday, we talked about the role of cell surfaces in mineral precipitation. And obviously the theory goes that the cell surface should act as a nucleation substrate via the negative surface charge at these pHs, which we see, and also the large surface area that these cell surfaces offer. So we really wanted to see if there was a role for the cell surface within these particular reactions. Now, obviously, this is kind of the hypothesis. What's the role of the cell surface? Simply put, we have the cell releasing urease. So we generally see a concentration gradient of inorganic carbon and urease away from the cell surface. And that would therefore suggest that we end up with essentially a gradient moving away from the cell surface, where we have a saturated zone right close to the cell surface relative to an unsaturated zone further away. So we would expect greater saturation near the cell surface and thus precipitation actually on the cell surface itself. Now, we've done work on this, and we can show that this is the case. Here's some TEM images of the early precipitation phase of Sporus pastori, demonstrating that there is active nucleation on the cell surface, and that over time, though, that this nucleation ultimately inactivates the cell. We can see here that these are effectively calcium carbonate crusts forming around the individual cells here. And in a sense, what this does, of course, is that it inactivates the cell because it can no longer reach the urea that it requires to hydrolyze. So in a sense, we're quite interested in what's the role of the cell surface over longer duration? How does this precipitation propagate? And really, is the cell mineral surface important throughout the whole precipitation process, not just at this initial stage? So if we look at, here we did some experiments using dialysis membranes, really to try and create experiments where we would have a cell-inclusive zone and a cell-free zone, but under the same broad chemical conditions, okay? So, and what we were able to do is really observe the carbonate crystals formed at the beginning of the experiment on day 1 and day 7, and really looked at the crystals formed in the bacteria-free, this is artificial groundwater, and the bacteria-inclusive artificial groundwater, okay? And we generally see that the mineralogy and general morphology of the calcium carbonate precipitates is the same in both the zones of the reaction. So in both the bacteria-free and the bacteria-inclusive zones, okay? So it kind of seems that the presence of cells doesn't actually affect the mineralogy or general morphology. However, if we actually look at the evolution of the crystal size distributions, we see an evolution of different crystal size distributions in the bacteria-free and the bacteria zone over time. And in fact, we generally see that after about a week, we see that the bacteria-inclusive zone, broadly shown by the dashed line here, has a much larger median mean crystal size, around 60 microns, compared to the bacteria-free zone, which is around 40 microns. Now, broadly, even though we have the same bulk chemistry in the bacteria-free and the bacteria-inclusive zone, it seems that ultimately microscale reactant supply limitations in the bacteria-free zone leads to smaller crystals in the bacteria-free zone compared to the bacteria-inclusive zone. More interestingly as well, though, is that actually when we actually look at the crystals formed, we ultimately see, in particular if we look at the image down here, that we're getting rather large crystals formed, which are encasing the cells. So it really seems that while we can show, obviously, from the initial nucleation phase that the cell surface is important, it really seems that we go from a cell interaction process initially, So we get nucleation on the cell surface, ultimately to a solution that's really dominated by reactions in the bulk solution, where we're getting growth on established crystals as a route to the main increase in crystal mass within these systems. So over time, it seems that there's less influence of the cell surfaces. So this really made us think, well, what is the role or not really of the cell surface in relation to larger scale engineering applications in the subsurface, okay? Obviously, up to now, we're talking broadly about diffusion-based processes, but clearly advection and diffusion will be important in flowing groundwater systems, which is the area of interest for us in particular. Now, this really led on to our interest in using biofilms and ureolytic bacteria as a driver for potential use in geologic carbon storage applications, both for mineralizing CO2 by mineral trapping, okay, as well as actually forming mineral barriers as a way of potentially reducing leakage pathways through the cap rock, but also in the well casings. One of the big problems with gas leakage from the subsurface is fractures within the well casings and fractures within cements in particular. So one big problem, as I'll come back to, is the oil industry really struggles with this using normal commercial cements. And so our interest really was, can we use this as, in a sense, as a fine biocement to seal these subsurface pathways? Now, some of the early work here just showing basically looking at how ureolysis-based carbonate precipitation may actually co-precipitate gaseous CO2. So here we've just performed some microcosm experiments with 99% 13C CO2 as a way of trying to distinguish between urea-based carbonate and CO2-based carbonate in the headspace, really to look at how do we get transfer from the gas phase through to the mineral phase. And we see that the incorporation of carbonate from the gaseous CO2 phase into calcite increased with increasing partial pressure of CO2, as well as increasing urea concentrations, up to around 40%. Now, while we're obviously forming calcium carbonate and we're showing that there is diffusion from the gas phase into the carbonate mineral, ultimately, of course, the moles of calcite precipitated are broadly equal to the moles of urea derived from the urea itself. So obviously you don't get any net precipitation of CO2 in the calcium carbonate. So, in a sense, for mineral trapping, this particular mechanism doesn't hold any great weight. But if we actually look at the solution chemistry, and here's just some modeling work looking at what's actually going on with the organic carbon speciation over time, we can actually see that so effectively, this just indicates the progression of hydrolysis and the changes in calcite mass, pH, the amount of DIC in solution, and the CO2 gas in the headspace. And what we actually see over time, as we induce precipitation via hydrolysis, we actually see that this actually enhances the overall the overall trapping of dissolved carbonate in solution and an associated decrease in carbon dioxide in the headspace as ureolysis develops. So ultimately, it seems like the pH increase driven by the ureolysis ultimately enhances the solubility trapping capacity of these artificial brines, which we used in this particular experiment. So there is some potential in relation to enhancing the solubility trapping of injected CO2. However, what we wanted to do was move on from looking just at the gas solution side of things. And as I mentioned, we're really more interested in the role of the microbe-mineral interface on microbially induced carbonate precipitation for ultimately plugging leakage pathways in particular. And really, this is likely to be occurring, obviously, in natural environments under advection flow conditions. We can't just do this in simple microcosms. We have to look at this under flow conditions. So this is really when we start to think about the role of biofilms and cells detached to surfaces rather than wholly planktonic phases. And this is really where we went from the microcosm to flow reactors and then to the field. So firstly, we started looking at simple sort of macro scale investigations and then upscaling. And really we just looked at, so firstly, we just looked at simple reactors where we could observe carbonate precipitation over flow paths. So this is really inoculating a flow cell here with the organism, and then flowing effectively urea and calcium-rich media through the reactor and observing carbonate precipitation down the flow path. Okay. Now, what we clearly see is we see mineralization is very apparent. We see a gradient in crystal size down the reactor. Okay. And clearly, it seems that this is ultimately a reactant supply limitation issue. So obviously upstream, there's a greater reactant supply of calcium and urea. And as we go further downstream, this is depleted. So we see greater crystal sizes at the inlet of the reactor rather than the outlet. And ultimately, these kind of reactions led to the complete plugging of the reactors in a very short space of time. So it shows that it's very successful. We can use MICP to ultimately plug reactors under advection and diffusion conditions, but it's not so good if we want to ultimately control and prolong mineralization as an engineered strategy in the surface. Okay, and it really also really demonstrated how what appears to be from the previous microcosm work to be initially driven by cell mineral nucleation and interactions. At this scale, then it really seems to get overtaken by bulk mineralization on existing mineral surfaces and other surfaces in solution. So really, we wanted to look at this further to see, what was going on in relation to microbe-mineral interactions at this scale. Now, here we started to use flow reactors, capillary flow reactors, and ultimately allowed us to undertake confocal microscopy in real time to look at the association of cells here in green and the carbonate precipitates in white here. And it's obviously we can see that there are cells on the reactor surface and we see the crystals grow. But ultimately, we also see more cells associated with the precipitated crystals, okay, than we do with the wider reactor surfaces. So it seems that there's ultimately preferential association with calcium carbonate, where we get growth and encasement repeating, where ultimately the growth of cells seems to exceed the encasement. So what we see here, for example, is we see these calcium carbonate crystals encrusted with Sporosacina pasteurii, but we get continuing carbonate precipitation occurring. So it ultimately seems that the initial direct nucleation on the cell surface occurs, but over time, crystal growth and cell growth continues preferentially on the underlying carbonate to ultimately produce these large carbonate cell masses. So moving on, given that, it seems that the cell mineral interaction is in some respects at the larger scale less significant, this bulk scale precipitation, in relation to utilizing it for carbon capture and storage, we needed to really work under high pressure conditions and also in the presence of supercritical CO2. So we started to think about this. Can these cells operate under high pressure and supercritical conditions? And this is really where we start to break away from the pure science to more the applied science. And we started to develop high pressure systems where we could flow supercritical CO2, so we could flow calcium and urea through at very high pressures, about 80 bar, to see if we can induce ureolysis, we can induce carbonate precipitation, and ultimately will the cells survive. And we see over time we can ramp the pressure up, and under these conditions we see that pH goes up, we see ammonia production continuing under these high pressure conditions, and we see significant colony forming units within the reactor effluent. So we basically see that these organisms are living and surviving and operating under high pressure conditions. And we see that carbonates very effectively precipitate out of solution over time. We can easily see the carbonates forming within these systems, and you can see these are large crystals that are forming. These have gone beyond the initial nucleation scale of the cell surface, and we're forming large bulk calcium carbonate precipitates. Of course, though, we're worried about plugging the inlet, so then we had to start developing strategies to avoid inlet plugging. And this just started to move away from constant flow conditions to more pulse flow conditions, where we ultimately were switching between medias, which included calcium and urea to ultimately produce mineral, and then effectively calcium and urea-free solutions in order to ultimately move through the highly saturated media and therefore stop nucleation. So we could effectively avoid plugging at the point of injection and control mineralization over a larger area. If we then looked at how permeability was affected by these the carbonate cements produced in porous media, we were then able to do this under high pressure conditions as well. And under the similar pulse flow conditions, we saw really up to around a 99% reduction in permeability, and we also avoided significant inlet plugging. So basically, the organisms can happily operate under these high pressure conditions. They can withstand supercritical CO2, and they can effectively reduce the permeability. And this was a sandstone, a Berea sandstone that was used here. And we generally see the permeability of the influent and effluent is broadly similar. There is a slight change, but ultimately we are avoiding inlet plugging by this pulsed injection strategy. We're then interested in moving up scales. So this is where we started to look more at radial flow. So of course, when you inject down an injection well in a field, you're often going to get a radial flow out from a well. So we developed a high pressure reactor. This was a bit of a beast. This is about 1 meter across. And this has allowed sampling from discrete locations, really to look at how this operated under deep subsurface conditions. And we were able to see, again, it worked very effectively. Here on the picture, you can see a carbonate crystal forming at the edge of this. This has been fractured, and we can actually see carbonate crystal plugging of this fracture zone in this Berea sandstone. So it seemed to effectively work. And again, we were able to show very significant decreases in permeability. Again, 3 orders of magnitude decrease in permeability through this pulse flow injection strategy. Now, we were lucky to get some, so we could show that this worked. It worked in the lab, we'd upscaled it. So now we're lucky to get funding from the US Department of Energy, really to take this to the field, primarily to look at CO2 leakage reduction through the sealing of leaking wells. And this is where we went from the lab to the field. We developed a mobile lab, which allowed upscaling of effectively microbial growth. We could produce around 100 gallons of microbes a day. It was a nice piece of kit, and it allowed us to really move in the field and basically work on different wells in different locations.
Now, you've got 5 minutes.
It did feel a little bit Breaking Bad. You know, it was a bit like a mobile meth lab. And I would say that Arwyn Edwards, who's a co-worker on this, he did some nanopore work when we were working in Alabama on this, looking at the response of native populations to injecting, obviously, large amounts of Sporus acina into the subsurface. So I can talk to others of you about that on the chat later if you want to know more about that work. But I'm running out of time, so I'll quickly wrap through this. We took it to the field. We're ultimately interested in sealing the wellbore cement in a fractured zone and leaking wells. We developed various injection strategies to inject media, but so effectively a cementing media with calcium and urea, and a calcium and urea-free media to allow us to push that mineralization media further into the formation. We're able to produce various ways to upscale the production of Sporus acina in situ. Here you can see we've got a number of cone tanks and heaters, so we can upscale cell production in the field. And here's the well we worked on in Alabama recently. This is one of many wells that we've undertaken this. And again, it was very successful. This is just showing well pressure and flow rate. And over time, we can see that ultimately the pressure increases and the flow rate decreases as we successfully seal this leaking well using these microbially formed minerals. And this resulted in around a 94% reduction in injectivity. These are log scans that show minerals forming. Basically, the orange area here, this is before and after, and the increase in the orange area shows the carbonate mineral formed in the subsurface. This is about 400 meters below the surface. Again, so showing that we are forming these carbonate minerals in situ proximal to the leaking well. This is really when it really went to the next stage, the commercial. One of the co-workers on this, Randy, then has opened up a commercial business using this application, taking it around the US, basically sealing commercial wells. Now, unfortunately, this is not for CO2 storage, but it is ultimately for gas-producing wells to bring them back online. So in a way, for myself, obviously interested in mechanisms to reduce the use of fossil fuels, or at least reduce their impact, it's slightly counterproductive because ultimately we're trying to reduce the use of gases overall. But I guess ultimately we're still reducing greenhouse gas leakage overall. And really, that is the main points of the talk. I just wanted to quickly mention, just a final point. So back to the ultimate role of the cell interface. While the early work then indicated a clear role for the cell interface, obviously in this applied upscale setting, it seems that bulk precipitation controlled by extracellular urease is ultimately more important. So that's why we've been working at other mechanisms, not just using cells and cells, but other sources of urea enzymes, and also thermally induced carbonate precipitation, inducing thermally induced urea precipitation. Sorry about going on. Here's some of the acknowledgements, and here's some of the co-workers in the field. Thanks a lot.